Have you ever stopped to wonder where everything around us truly comes from? The air we breathe, the ground beneath our feet, even the very atoms that make up our bodies, they all share an extraordinary origin story written in the stars. Out there, in the silent depths of space, something magical is happening. Tiny particles of stardust, forged in the hearts of ancient suns, are journeying back to the place they were born. This isn't science fiction. It's a real, ongoing process, a cosmic homecoming that has been repeating for billions of years, and it's one of the most beautiful and fundamental cycles in the entire universe. Think about that for a moment. The same stardust that once swirled inside a giant star that witnessed a supernova's brilliant death is now drifting through vast clouds of gas and dust stellar nurseries where new stars and planets are coming to life. This journey isn't random. It's part of a grand, intricate dance guided by gravity, chemistry, and time. And it's this very process that makes life possible. Without stardust returning to its birthplace, there would be no Earth, no solar system, and certainly no us. We are, in the most literal sense, children of the cosmos. In this video, we're going to trace that incredible voyage from the explosive death of a star to the quiet, dusty cradles where new worlds are born. We'll explore how stardust shapes star formation, seeds planets with the ingredients for life, and connects us all to something much larger than ourselves. This is more than astronomy. It's a story of renewal, of beginnings rising from endings, and it holds profound clues about our own place in the universe. So settle in, open your mind to wonder, and let's begin this journey together back to the stars and back to ourselves. To truly grasp the profound journey of stardust returning to its birthplace, we need to start with the magnificent life cycle of the stars themselves. Think of a star not as a distant, unchanging point of light, but as a dynamic, living entity with a beginning, a middle, and an end, a story written in fire and gravity. Every star begins its life in a stellar nursery, a vast, cold, and incredibly beautiful cloud of gas and dust known as a nebula. These cosmic cradles are scattered throughout our galaxy, immense and often illuminated by the newborn stars within them. For a star to be born, a small pocket within this nebula must begin to collapse under its own gravity. This isn't a fast process. It can take hundreds of thousands of years for this pocket to condense, heat up, and finally ignite the incredible engine at its core, nuclear fusion. This is the moment a star truly turns on, fusing hydrogen atoms into helium and releasing the tremendous energy that makes it shine. A star's life is a constant, delicate battle between the inward crush of gravity and the outward push of radiation from fusion. The length and nature of this battle depend entirely on the star's mass. A massive star, many times heavier than our Sun, lives a spectacular but short life. It burns through its fuel with furious intensity, shining with a brilliant blue-white light for only a few million years. In its core, it becomes a cosmic forge, creating heavier and heavier elements through fusion carbon, oxygen, neon, and eventually iron. Our own Sun, a medium-sized star, is far more temperate. It has been shining steadily for about 4.5 billion years and will continue for billions more, patiently converting hydrogen into helium and providing the stable energy that made life on Earth possible. But all stars, regardless of their size, must eventually run out of fuel, and how a star dies is one of the most important events in the cosmos. For stars like our Sun, the end is a beautiful and relatively gentle transformation. As its core fuel depletes, it swells into a red giant, its outer layers puffing out into space to form a glowing shell of gas and dust called a planetary nebula. At the heart of this nebula, the star's core remains as a white dwarf, a dense, Earth-sized ember that slowly cools over eons. For the massive stars, death is far more violent and spectacular. When they can no longer support their own immense weight, their cores collapse catastrophically and then rebound in a shattering supernova explosion. This titanic event can, for a brief moment, outshine an entire galaxy. It is in these incredible blasts that the universe forges the heaviest elements like gold, silver, and uranium, and then hurls them, along with vast amounts of other newly created stardust, out into the void at nearly the speed of light. This is the crucial moment for our story. This ejected material, enriched with the elemental building blocks of planets and life, doesn't just vanish. It spreads out, mixing with the surrounding interstellar medium. It becomes the next generation of raw material. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of it was forged in the heart of a long-dead star and scattered across the galaxy by its death throes. This stellar life cycle is the ultimate act of cosmic recycling. Each generation of stars builds upon the ashes of the ones that came before, ensuring that the universe is constantly evolving, growing more complex, and creating the conditions for new stars, new planets, and ultimately, new life to emerge. Now, let's get specific about what we're actually talking about when we say stardust. It's a word that sounds almost magical, and in a way it is, but it's also something very real and physical. This isn't just a cloud of gas or a faint shimmer of light. Stardust is made of countless billions of tiny, solid particles. We're talking about grains so small they're often microscopic, finer than the finest powder you could ever imagine. Each one is a tiny, tangible piece of a star, and they are everywhere. So, what are these minuscule grains actually made of? Their composition is a direct record of the star that created them. Many are silicates, which are minerals built around silicon and oxygen, the same fundamental stuff that makes up a huge portion of the Earth's crust and even the sand on a beach. Others are grains of graphite, a form of pure carbon. Think of the lead in your pencil, that's graphite. But out in space, these carbon atoms can arrange themselves into even more incredible structures, forming tiny diamonds or soccer ball-shaped molecules called fullerenes. Some of the most fascinating types of stardust are rich in carbon and hydrogen, forming complex organic molecules known as polycyclic aromatic hydrocarbons. These PAHs are considered some of the basic building blocks for the chemistry that leads to life. So within these specks of dust, we have the seeds of both rocks and biology. Finding this dust might seem like looking for a needle in a cosmic haystack, but astronomers have clever ways of spotting it. When a large cloud of stardust drifts in front of a bright nebula or a distant star, it doesn't let the light pass through. Instead, it blocks it, creating beautiful, intricate dark patches against the glowing background. The iconic Horsehead Nebula is a perfect example of this. That famous silhouette is actually a massive cloud of stardust, backlit by the bright gas behind it. When we point telescopes like the James Webb Space Telescope at these dark regions in infrared light, we can see them actually glowing with the heat from these countless dust grains, revealing the hidden structures within. But how do we go from seeing it from afar to truly knowing what it's made of? That's where the real detective work begins. Scientists use a technique called spectroscopy. When light from a star passes through a cloud of dust, the dust absorbs specific wavelengths of light, leaving behind a unique fingerprint in the spectrum. By analyzing these fingerprints, we can identify the exact elements and molecules present, almost like taking the dust's chemical signature from millions of light years away. And even more astonishingly, we can actually hold pieces of it in our hands. Inside certain primitive meteorites that have fallen to Earth, scientists have found presolar grains, tiny particles that are actually older than our solar system. By analyzing these grains with incredibly precise instruments, we can trace them back to the specific types of stars they came from, whether it was a red giant, a supernova, or another kind of stellar factory. This makes stardust not just a theoretical concept, but a physical sample of another star, a piece of another time and place that we can study right here in a laboratory. This is why stardust is so fundamentally important. It is the universe's ultimate raw material. It's the flower in the cosmic kitchen. Without it, nebulae would just be clouds of gas, unable to cool down efficiently enough to collapse into new stars. Without it, there would be no solid particles to clump together and form planets, asteroids, or comets. Every rocky world, every icy moon, every speck of dirt in every solar system began its existence as stardust drifting through the void. It is the literal foundation upon which planets are built, and the essential ingredient that makes the universe not just a collection of glowing balls of gas, but a place of substance, complexity, and potential. Now let's journey into the very heart of these cosmic cradles, the places where all this stardust is destined to return, the stellar nurseries. If the life cycle of a star is a story, then these nebulae are the bustling, chaotic, and breathtakingly beautiful chapters where new characters are introduced. Picture the most immense, diffuse clouds you can possibly imagine, not puffy white things in our sky, but colossal structures light years across, composed almost entirely of hydrogen gas and that all-important stardust. They are the nurseries of the galaxy, and they are far from quiet, empty places. They are dynamic, turbulent, and alive with the raw energy of creation. Some of these nurseries are famous, familiar even to casual stargazers. The Orion Nebula, a fuzzy patch in the hunter's sword, is a perfect example. Through a telescope, it's not just a smudge. It's a glowing, churning cauldron of pink and blue gas, illuminated from within by a cluster of brilliant, newborn stars called the trapezium. Then there's the Carina Nebula, an even larger and more violent stellar factory, home to some of the most massive and unstable stars known, including the volatile Eta Carinae. These regions aren't just pretty pictures, they are active construction zones, and their visibility offers us a front-row seat to the ongoing process of star birth. But these nurseries don't just spontaneously decide to start making stars. They often need a cosmic push, a trigger to upset the delicate balance. A cloud of gas and dust can drift peacefully for eons, but when a shockwave from a nearby supernova slams into it, or when two clouds collide, the effect is dramatic. It's like squeezing a handful of airy snow in your glove. The material gets compressed, its density increases tremendously, and gravity suddenly gets a much stronger grip. This compression creates pockets of higher density within the cloud. These pockets, often called dense cores, are the seeds of future solar systems. As gravity pulls more and more material inward, these cores begin to heat up, spinning faster and faster, flattening into a disk shape with a growing, glowing ball at the center, a protostar. The environment around this newborn protostar is anything but calm. Powerful magnetic fields channel material into jets that shoot out from the poles at incredible speeds, while the surrounding disk of gas and dust, the protoplanetary disk, swirls like a cosmic whirlpool. It is within this spinning disk that the true magic for planet formation happens. Those tiny grains of stardust we've been following, the ones that journeyed across space, are now here. They collide, stick together, and begin to form ever larger clumps, from pebbles to rocks to planetesimals, all within the safety of this dusty disk. The young star at the center begins to clear a cavity around itself with its fierce stellar wind, but further out, the stage is set for the birth of planets. This entire process, from initial collapse to a shining new star, is a delicate dance governed by the fundamental forces of physics and enriched by the ancient stardust that has finally, after its long voyage, come home. So how does this precious stardust, forged in the fiery hearts of stars, actually break free and begin its journey across the cosmos? It turns out, the method of escape depends entirely on the star's personality, its mass, and how it chooses to end its life. For stars like our Sun, the ending is a slow, elegant, and truly beautiful farewell. After billions of years of steady fusion, a Sun-like star begins to run out of hydrogen fuel in its core. This triggers a dramatic transformation. The star swells to hundreds of times its original size, becoming a red giant. In this bloated, unstable state, its gravitational grip on its outer layers weakens significantly. This allows powerful stellar winds to simply blow those layers away, particle by particle, atom by atom. These winds carry gas and newly formed dust grains outward, creating a vast, expanding shell of material. This isn't a chaotic explosion, but more of a gentle, continuous puffing away of the star's atmosphere. As this shell expands and the hot, exposed core of the star begins to emit intense ultraviolet radiation, it illuminates the ejected material from within. The result is one of the most stunning sights in the universe, a planetary nebula. Despite the name, these have nothing to do with planets. They are the glowing shrouds of dead stars, intricate tapestries of color and light woven from the very essence of the star itself. The famous Ring Nebula and the Helix Nebula are perfect examples of this cosmic bubbles of gas and dust that will slowly dissipate over tens of thousands of years, leaving behind only the white dwarf core. But for the universe's true heavyweights, the massive stars, death is not a gentle sigh but a cataclysmic scream. These stars live fast and die young, ending their short, brilliant lives in the most violent event since the Big Bang itself, supernova. When a massive star can no longer support itself against its own immense gravity, its core collapses in less than a second. This collapse triggers a titanic shockwave that races outward, violently blasting the entire star apart. The energy released is almost unimaginable. For a brief moment, a single supernova can outshine an entire galaxy of billions of stars. In this incredible inferno, temperatures and pressures reach levels so extreme that every element in the periodic table is forged, from the iron in our blood to the gold in our jewelry. The supernova then hurls this newly created treasure trove of elements and vast quantities of dust out into space at speeds reaching tens of millions of kilometers per hour. This explosive ejection is the primary way the universe distributes heavy elements, seeding entire galaxies with the raw materials for new stars, planets, and life. The Crab Nebula is the remnant of such an event, a tangled web of expanding debris that Chinese astronomers observed as a guest star in the sky in the year 1054. Even today, nearly 1,000 years later, we can still see that cloud expanding, a testament to the sheer power of a star's final act. Beyond these two primary methods, there are other fascinating ways stars contribute to the cosmic dust supply. In binary star systems where two stars orbit each other closely, material can be stripped from one star and transferred to its companion, often creating dusty disks and outflows in the process. Some extremely hot and massive stars, known as Wolf-Rayet stars, experience such powerful winds that they effectively peel away their own outer layers, ejecting huge amounts of carbon-rich dust into their surroundings. Even the intense environments around supermassive black holes can generate outflows that contain dust. everywhere we look, stars are in the business of recycling themselves, ensuring that the story of one generation becomes the foundation for the next. Once freed from its dying star, a particle of stardust doesn't just float idly in one place. It embarks on an epic, solitary voyage across the unimaginable distances between the stars. This journey takes place in what we call the interstellar medium, which sounds like a complex term, but it really just means the space between stars. And contrary to what you might think, this space isn't a perfect vacuum. It's actually filled with a very thin soup of gas, mostly hydrogen, and most importantly for our story, countless billions of these tiny dust grains. Each one is like a microscopic spaceship setting off on a trip that could last for millions of years. The forces guiding this journey are subtle but powerful. One of the most fascinating is radiation pressure. Stars don't just emit light, they emit a constant stream of photons, tiny particles of light that actually exert a physical push. For a grain of stardust floating near a star, this gentle pressure acts like a cosmic breeze, slowly but surely pushing it away. It's not a violent shove, but a persistent force that can accelerate dust grains over immense timescales, helping them travel from one part of the galaxy to another. Then there's gravity, the great architect of the cosmos. The collective gravitational pull from stars, gas clouds, and even the invisible dark matter that permeates the galaxy gently tugs on these particles, guiding them along invisible pathways. They might be drawn towards the spiral arms of our Milky Way, where matter is more densely packed, or they could be influenced by the passing gravity of a star, which acts like a slight gravitational lens, bending the dust's trajectory ever so slightly. Adding another layer of complexity are the magnetic fields that weave their way throughout our galaxy. These invisible lines of force can cause electrically charged dust grains to align and even spiral along them. Imagine a tiny iron-rich dust grain acting like a microscopic compass needle, orienting itself within this vast magnetic tapestry. This doesn't necessarily propel the dust, but it guides and influences its direction, ensuring its journey isn't entirely random. Drifting at speeds that might seem slow to us, these particles cover vast distances over their incredibly long lifetimes. They might wander for eons, but eventually, many will encounter something new, perhaps the tenuous outer fringe of a giant molecular cloud, a region of space that is far denser than the void they've been traversing. This journey, however, is fraught with peril. The interstellar environment is a harsh and unforgiving place. Cosmic rays, which are atomic nuclei accelerated to nearly the speed of light by distant supernova and black holes, constantly bombard these dust grains. A direct hit from a high-energy cosmic ray can blast atoms right off the surface of a grain, slowly eroding it away in a process called sputtering. Or it could shatter the grain entirely, breaking it down into even smaller fragments. Intense ultraviolet radiation from hot, young stars can also break apart the molecular bonds on the surface of the dust, altering its chemical composition and stripping away any fragile icy mantles it may have accumulated. Despite these constant threats, a remarkable amount of stardust survives this gauntlet. The hardiest grains, perhaps those with a robust crystalline structure forged in the extreme conditions of a supernova, press on. They are the cosmic survivors, carrying within them an unaltered record of their birthplace. Their very composition, the specific ratios of isotopes of elements like oxygen, carbon, and silicon, acts as a chemical fingerprint, a piece of forensic evidence that allows astronomers to trace them back to the type of star that created them, even billions of years later. This incredible resilience means that these tiny messengers can travel from one side of a galaxy to another, ensuring that the elements created in one generation of stars can be delivered to the nursery of the next, forever enriching the galaxy with each epic voyage. After surviving the harshness of interstellar space, these resilient dust grains face a new chapter in their journey, one governed by the most fundamental and pervasive force in the universe, gravity. Think of gravity not as a simple pull, but as the great cosmic architect, the invisible hand that sculpts the large-scale structure of everything we see. It's the force that built the galaxies, the force that holds our solar system together, and it is absolutely essential for gathering scattered stardust and bringing it home. Without gravity's persistent, patient influence, these particles would simply drift forever in the void, their potential forever unfulfilled, and the cycle of cosmic renewal would grind to a halt. So how does this work on the scale of a single dust grain? Imagine a tiny speck of silicate or carbon, perhaps a millionth of a meter across, drifting on the outskirts of a vast molecular cloud. This cloud itself is a gravitational well, a region of space where mass is concentrated, creating a gentle but insistent pull on everything around it. Our dust grain, feeling this tug, begins a slow, steady migration inward. It's not a dramatic, swift fall. It's a gradual sinking, like a single leaf slowly spiraling its way down to settle on a forest floor. This process of accumulation is critical because it's how these nebulae grow denser and more massive over time, eventually reaching the point where they can collapse under their own weight to form new stars. Every particle that joins the cloud adds to its gravitational influence, making it even more effective at pulling in more material, a beautiful, self-reinforcing feedback loop of creation. But the story doesn't end with a single cloud's gravity. The scale of this gravitational guidance is truly mind-boggling. Our entire galaxy, the Milky Way, is rotating, and its spiral arms are not static structures but rather waves of density like cosmic traffic jams. As a dust grain travels through the galaxy, it can be swept up by one of these density waves. The gravitational environment within a spiral arm is far stronger, compressing gas and dust and dramatically increasing the chances of that dust being funneled into a waiting stellar nursery. Furthermore, the gravitational tides of the galaxy itself, the subtle pull from the collective mass of billions of stars, acts as a constant, background force that helps to shepherd material into the right neighborhoods for star formation. Even more mysterious and fascinating is the role of dark matter. While we cannot see it directly, we know this enigmatic substance makes up the vast majority of the galaxy's mass. Its gravitational influence is immense, forming a massive, invisible halo that envelops the entire Milky Way. This dark matter halo helps to shape the overall structure of the galaxy, and in doing so, it creates gravitational pathways and currents that guide the flow of interstellar material, including our stardust. Then there are the chance encounters with passing stars. As a star moves through a region, its gravity can create a temporary wake, pulling nearby dust along with it, much like a boat creates a ripple that carries leaves and debris in its path. All of these large-scale forces, spiral density waves, galactic tides, dark matter halos, and stellar flybys, work in concert, creating a complex and dynamic gravitational web that ensures no stardust's journey is ever truly random. It is being guided, nudged, and directed on a billion-year voyage to a specific destination, a place where it can finally help build something new. Inside the relative calm of a dense nebula, the journey of our stardust takes a dramatic and utterly transformative turn. This is no longer a story of solitary drifting. It becomes a tale of connection, collaboration, and construction. The nebula is a bustling, crowded metropolis compared to the empty interstellar highways, and our dust grain is about to become a vital part of the building crew. The first step in this new phase is deceptively simple: a collision. But these aren't the violent, shattering crashes you might imagine. Within the dense, cold heart of a molecular cloud, particles are moving relatively slowly. Their collisions are more like gentle, almost slow-motion bumps, and in this gentle environment, something remarkable happens. They stick together. This sticking power comes from fundamental forces at the tiniest scales. Electrostatic forces, the same kind that makes a balloon stick to your hair after you rub it, can cause two dust grains to cling to each other after a bump. Even more fascinating are van der Waals forces, which are weak electrical attractions between the atoms on the surfaces of two closely adjacent particles. It's a bit like how two slightly moist grains of sand might stick to your finger. While each individual bond is incredibly weak, together they create a powerful adhesive effect at the microscopic level. This process, the gradual sticking together of smaller particles to form a larger one, is what astronomers call accretion. It's the universe's way of turning fine cosmic flour into dough, one tiny collision at a time. What begins as two microscopic specks sticking together quickly snowballs. This new, slightly larger aggregate now has a bigger cross-section, making it an easier target for other particles. It collides with more silicate grains, some carbon flakes, perhaps a grain coated in a tiny shell of water ice. Each collision adds mass and complexity. Over hundreds of thousands of years, these aggregates grow from microscopic specks to millimeter-sized particles, then to centimeter-sized pebbles. You can think of it like a cosmic game of Katamari Damacy, where a small ball rolls around, picking up everything in its path and growing ever larger. Within the swirling protoplanetary disk surrounding a young star, these pebbles begin to behave in incredible ways. As they orbit the newborn sun, aerodynamic drag from the surrounding gas causes them to drift inward, and in doing so, they sweep up other pebbles, accelerating their growth exponentially. This is where the story shifts from simple dust to the birth of worlds. These pebble-sized aggregates are now large enough that their own minuscule gravitational fields begin to play a role. They can pull in more material, and when they collide with other similar-sized objects, they are more likely to merge than to shatter. Through this relentless process of collision and merger over millions of years, these objects graduate from pebbles to rocks, then from rocks to mountain-sized bodies called planetesimals. These planetesimals are the true building blocks of planets, the asteroids and protoplanets, that will eventually collide and gravitationally interact to clear their orbits and form the terrestrial worlds like Earth, Mars, and the cores of giant planets like Jupiter. The composition of the original Stardust is absolutely crucial here. A nebula enriched with carbon-rich dust from ancient red giant stars might eventually form planets rich in graphite and other carbon compounds. In contrast, a region seeded with silicate-heavy dust from supernova will tend to form rocky, Earth-like worlds. The very chemistry of future planets and their potential to host life is being determined right here in these gentle, microscopic collisions within the dusty dark of a stellar nursery. But this is where the story gets even more fascinating, because the journey of Stardust isn't just a physical one. It's a profound chemical metamorphosis. As our hardy grain of stardust finally crosses the threshold into the dense, cold heart of a nebula, it enters an environment that is a spectacular cosmic chemistry lab. The temperature here can plunge to just a few dozen degrees above absolute zero, and the density of gas and other particles increases dramatically. In this frigid, crowded environment, our dust grain ceases to be a simple, inert speck of rock or carbon. It becomes a catalyst, a template, and a construction site for an incredible array of new molecules, some of which are the very precursors to life itself. The first thing that happens is a process called freeze-out or accretion. Atoms and molecules from the surrounding gas, things like water vapor, carbon monoxide, ammonia, and methane that are zipping around in the void slowly lose their energy in the cold. When they bump into the surface of our dust grain, they don't just bounce off. Instead, they lose their remaining kinetic energy and stick, freezing directly onto the grain's surface in a process known as deposition. Over time, our once bare speck of silicate or graphite becomes encased in a thick, icy mantle. Imagine a tiny pebble being left outside on a cold, humid night, gradually becoming covered in an intricate layer of frost. That's exactly what's happening on a microscopic scale, but this cosmic frost isn't just water ice. It's a complex cocktail of ices, a frozen zoo of simple molecules that are now locked together on this tiny stage. This icy coating, however, is far from inert. It is about to become the site of some of the most important chemistry in the universe. Remember those brilliant, massive young stars, the trapezium cluster in Orion, for example, that are blazing at the heart of the nebula. They are pouring out immense amounts of ultraviolet radiation. This high-energy light acts like a cosmic blowtorch, but instead of just melting the ice, it energizes it. When a UV photon smashes into the icy mantle, it breaks apart the fragile bonds holding those simple molecules together. This creates a soup of highly reactive fragments, ions and radicals, that are desperate to form new bonds. Trapped together on the surface of the dust grain, these fragments bounce around and randomly reconnect, but now in new, more complex arrangements. This process, known as photochemistry, is how simplicity begets complexity in the cold of space. From the simple building blocks of water, ammonia, and methane, this radiation-driven chemistry can produce ethanol, the alcohol in beer and wine. It can form formaldehyde, and even more excitingly, complex organic molecules like polycyclic aromatic hydrocarbons and the simplest amino acids, such as glycine. Think of it like this: the dust grain provides the solid workbench, the icy mantle provides the raw lumber and nails, and the ultraviolet radiation from the newborn stars provides the energy and the blueprint, allowing entirely new and more complex structures to be assembled. These newly formed molecules are the potential building blocks for life, and they are being manufactured in vast quantities on countless trillions of dust grains throughout every stellar nursery in the galaxy. But the chemical drama doesn't end with cold, slow photochemistry. Nebulae are also violent, dynamic places, shock waves generated by the explosive death of a nearby massive star in a supernova, or by the powerful bipolar jets screaming away from a newborn protostar, can rip through these cloudy regions. When one of these shock fronts slams into a pocket of dust, the effect is instantaneous and violent. The dust grains are suddenly heated, not over millennia, but in a flash. They can be warmed from near absolute zero to hundreds of degrees in a matter of seconds. This sudden thermal shock can cause a process called sintering, where the tiny particles that make up the grain begin to fuse together on their surfaces, altering the very texture and structure of the dust, making it more robust. In more extreme cases, the heat can be so intense that it flash evaporates the entire icy mantle we just talked about, blasting all of those newly formed complex organic molecules directly back into the surrounding gas. This might sound destructive, and it is for that particular grain's mantle, but it's actually a crucial delivery mechanism. It seeds the entire gas cloud with this rich soup of organic material, making it available to be incorporated into every new planetesimal and comet that forms in the region. So, through both gentle, cold chemistry and violent, hot processing, the humble stardust grain is transformed from a simple mineral into a vehicle of chemical complexity. It arrives as a relic of a dead star, but it becomes an active participant in creating the conditions for new worlds. The nebula becomes enriched, not just with the heavy elements forged in stellar furnaces, but with a dazzling diversity of new molecules. This chemical enrichment is the critical final step that takes a cloud of primordial hydrogen and helium and turns it into a well-stocked pantry, filled with all the ingredients necessary to build not just rocks and ice, but atmospheres, oceans, and ultimately, the chemistry that can one day spark into life. Now we arrive at a truly profound twist in our story, one that elevates stardust from a simple building material to an active, essential player in the cosmic drama of creation. Up to this point, our journey has followed stardust as a passenger, a piece of cargo ejected from a dying star and delivered by gravity to a new nebula. But once it arrives, it doesn't just sit on the cosmic shelf. It gets a job. It becomes a catalyst, a microscopic foreman on the construction site of a new solar system. And without its unique skills, the entire process of star formation would be far slower, far less efficient, and perhaps might not happen on the scale we see at all. To understand this catalytic role, we have to tackle a fundamental problem that every nebula faces, the heat problem. A giant cloud of gas, mostly hydrogen, wants to collapse under its own gravity to form a star. But as it collapses, the gas particles are squeezed closer and closer together. They bump into each other more frequently, and this bumping generates heat, much like how pumping air into a bicycle tire heats up the pump. This heat creates an outward pressure that fights against the inward crush of gravity. It's a classic standoff. For the cloud to win this battle and successfully form a star, it needs to find a way to shed this heat, to cool itself down so that gravity can finally gain the upper hand. This is where our stardust grains become the universe's ultimate radiators. A gas by itself is not very good at getting rid of heat. Its atoms are too spread out. But a solid dust grain is incredibly efficient at it. Each tiny speck of stardust acts like a miniature air conditioning unit. As the hydrogen atoms collide with a dust grain, they transfer their energy to it, they heat it up. The grain, now energized, radiates that heat away as infrared light, which easily escapes the cloud and shoots out into the coldness of space. This process effectively takes the thermal energy that was preventing the collapse, converts it into infrared radiation, and throws it out the window. With this cooling system now active, the internal pressure of the gas cloud drops dramatically. The balance of power shifts decisively in gravity's favor, and the cloud can collapse far more quickly and efficiently. It's the difference between trying to compress a hot, expansive gas and a cool, dense one. The stardust, by simply being there, breaks the logjam and allows the grand construction project to begin in earnest. But the dust's job description doesn't end there. It also has a critical second role as a matchmaker for the most important molecule in the universe, molecular hydrogen. A star runs on nuclear fusion, fusing hydrogen atoms into helium. But the vast clouds that form stars aren't made of isolated hydrogen atoms for very long. They need to form H2, two hydrogen atoms bound together, which is a much more stable and abundant form of the fuel. Here's the problem. Forming a hydrogen molecule is a very tricky, almost impossible thing to do out in the empty void of a gas cloud. If two hydrogen atoms meet in space, they might briefly stick together, but the bond formation releases a tiny burst of energy that actually forces them apart again before the bond can properly set. It's a frustrating cosmic catch-22. Once again, stardust provides the perfect solution. The surface of a dust grain acts as a catalyst, a neutral third party that facilitates the reaction. Imagine a tiny dance floor. That's the surface of the grain. One hydrogen atom drifts in and sticks to the surface, sitting there and waiting. Then, a second hydrogen atom arrives and sticks right next to it. Now they are held in place, neighbors on this microscopic dance floor. They can interact, and when they form that bond, the energy released isn't enough to launch them both back into space. Instead, it's transferred into the lattice of the dust grain itself, which vibrates slightly and radiates the energy away harmlessly. The newly formed, stable hydrogen molecule then simply drifts off the grain and back into the cloud. This process is happening on trillions upon trillions of dust grains simultaneously, tirelessly manufacturing the primary fuel for the next generation of stars. Without this catalytic surface, molecular hydrogen would form at a rate thousands of times slower, drastically putting the brakes on the entire star formation process. So, when we look at a glorious stellar nursery like the Orion Nebula, blazing with the light of newborn stars, we are not just looking at a place where stardust has gathered. We are looking at a place that stardust made possible. It is the unsung hero that cooled the gas and built the fuel. This transforms our understanding of the cosmic cycle from a simple story of death and rebirth into a far more sophisticated and beautiful narrative of interdependence. The elements created in the death of one star do not just become the bricks for the next. They become the very tools, the catalysts, and the enabling technology that allows the next star to be born at all. Stardust is not merely a product of cosmic evolution. It is one of its primary architects, a tiny but indispensable driver of the universe's ongoing creativity. Of course, the scientific narrative of Stardust's journey isn't just a beautiful theory. It's a story supported by a mountain of hard evidence, gathered by astronomers using some of the most advanced technology ever created. To actually see this process in action, to watch stardust drifting back into stellar nurseries, we have to look at the universe in a completely different light, literally. Our eyes are only sensitive to a tiny sliver of the electromagnetic spectrum, the part we call visible light, but much of the drama of stardust happens in wavelengths we cannot see, hidden behind veils of gas and dust. To pierce that veil, we rely on the incredible power of infrared astronomy. Think of a dust grain floating in a dark nebula. It's cold, but it's not at absolute zero. It still holds a tiny amount of heat, and that heat causes it to glow, not with visible light, but with a faint, warm signature in the infrared part of the spectrum. To our eyes, a cloud like the Orion Nebula might look like an impenetrable dark patch, but to an infrared telescope, it's a glowing, intricate landscape. Telescopes like the now-retired Spitzer Space Telescope and its magnificent successor, the James Webb Space Telescope, are specifically designed to be exquisitely sensitive to this infrared glow. They don't see darkness, they see the heat radiated by countless trillions of dust grains, allowing us to map their temperature, their density, and their distribution within these star-forming clouds with breathtaking detail. The iconic Pillars of Creation image from JWST isn't just a pretty picture. It's a direct infrared snapshot of stardust itself, illuminated and sculpted by the fierce radiation of newborn stars, showing us exactly where the raw materials for future planets are currently concentrated. But seeing the dust is only half the battle. We also need to know what it's made of and what's happening on its surface. This is where radio astronomy takes over. Giant radio dishes like those at the Atacama Large Millimeter Array in Chile tune into a different signal. They don't look for heat, they listen for the faint whispers of molecules. When a molecule like carbon monoxide or a complex organic compound like ethanol spins or vibrates, it emits a very specific frequency of radio wave, a unique spectral line that acts like a chemical barcode. By scanning a nebula and identifying these barcodes, astronomers can determine the precise chemical composition of the gas that's frozen onto the dust grains or has been recently released from them. This tells us that the ices coating these particles aren't just simple water ice. They're a complex cocktail of organics, and radio telescopes provide us with the recipe. Adding another layer to this detective work is a technique called polarimetry. Dust grains in space aren't always randomly oriented. They can be shaped like tiny needles or rods, and they often spin. The magnetic fields that permeate our galaxy can cause these non-spherical grains to align themselves, much like iron filings aligning with the field of a bar magnet. When light from a distant star passes through a cloud of these aligned grains, the dust preferentially scatters and polarizes that light. By carefully measuring the direction of this polarization with sensitive instruments, astronomers can actually map the invisible magnetic fields within the nebula. This is crucial because these fields play a huge role in guiding the collapse of the cloud and channeling the flow of material, directly influencing how stardust is gathered and where new stars will eventually form. All of these methods are incredible, but they share one thing in common. They are remote observations. We are studying these particles from millions of light years away. But what if we could actually hold a piece of stardust in our hands? Astonishingly, we can. Our solar system is constantly sweeping up interstellar dust as it moves through the galaxy. Even more directly, some of the most primitive meteorites that fall to Earth, like the Murchison meteorite, contain within them tiny, ancient grains that are literally older than our Sun. These are called presolar grains, and they are the true smoking gun. Using sophisticated lab techniques like secondary ion mass spectrometry, scientists can blast these tiny grains with an ion beam and analyze the specific isotopes of elements they contain. The ratios of these isotopes are like a forensic fingerprint. They are completely unique and can only be formed in the specific, extreme conditions inside a red giant star or the violent shockwave of a supernova. By studying these microscopic time capsules, we have direct physical proof that the dust in our solar system, the dust that formed our planet and everything on it, originated in the depths of other stars. This powerful combination of remote sensing and direct sample analysis weaves together a complete and undeniable story, confirming that the universe is not just expanding, but that it is actively and continuously recycling itself, with stardust as its primary currency. To witness this entire cosmic drama in action, we need look no further than the magnificent Orion Nebula, a sprawling stellar nursery hanging just below the famous Hunter's Belt in our night sky. Located a mere 1,300 light-years away, it is our closest large star-forming region, a proximity that transforms it from a distant mystery into a detailed, living laboratory. Within its glowing gases and dark, dusty lanes, we can observe every single step of the Stardust cycle we've been exploring, playing out in real time on a grand and breathtaking scale. It is the perfect case study, a place where theory meets observation and the abstract becomes stunningly tangible. At the heart of the nebula lies the engine of this entire operation, the trapezium cluster. This is a group of 4 incredibly brilliant, hot, and massive young stars, each many times larger and more powerful than our Sun. These stellar infants are less than 1 million years old, but they are already dominating their environment with a ferocious output of ultraviolet radiation and powerful stellar winds. This intense energy flood is the sculptor of the nebula. It carves out vast cavities within the gas cloud and does something truly magical to the surrounding stardust. It makes it visible. The same way a spotlight illuminates dust motes in a darkened room, the trapezium stars cause the countless dust grains to fluoresce, glowing in both visible and infrared light. This illumination is what creates the nebula's famous ethereal glow, but for astronomers, it's a spotlight on the main actor, allowing us to trace the distribution and movement of the dust itself. And what we see is a dynamic, chaotic ballet of forces. On one hand, the fierce stellar winds from these massive stars act like a cosmic leaf blower, pushing dust and gas outward, attempting to clear the region and even threatening to disrupt the formation of smaller, neighboring stars. The iconic proplyds, or ionized protoplanetary disks, seen in Hubble images are a direct result of this radiation, their material being photoevaporated and swept away. Yet counterintuitively, this violent expulsion is only part of the story. In other, denser regions of the nebula, shielded from the full brunt of the stellar fury, gravity is winning the battle. Here, observations from radio and infrared telescopes show dust grains are not being blown away. They are instead falling inward, sinking into deep gravitational wells. They are accumulating in these quiet pockets, gathering mass and beginning the slow, patient process of accretion that will one day lead to new protostars and planets. It's a cosmic tug of war with creation and destruction happening side by side. The spectroscopic data gathered from Orion is where the chemistry comes to life. By analyzing the specific wavelengths of light absorbed and emitted, scientists have identified a veritable factory of complex molecules frozen onto the surfaces of these dust grains. We're not just talking about simple ices, we're talking about the precursors to life. Molecules like water, carbon monoxide, and methanol are abundant. Even more complex organic compounds, including polycyclic aromatic hydrocarbons, have been definitively detected. These findings provide direct, observational evidence for the chemical processes we discussed, the icy mantles forming on grains and being processed by stellar radiation. The nebula is quite literally assembling the building blocks of future worlds, and perhaps future biology, right before our instruments' eyes. Perhaps the most compelling evidence of all comes from the intricate structures captured in stunning detail by the Hubble and James Webb Space Telescopes. We can see dark, dense pillars of gas and dust, like the famous pillars of creation in other nebulae, where the material is so thick it shields the interior from the outside radiation. Within these pillars, the conditions are perfect for stardust to do its work. We can observe Bok globules, which are small, dark knots of dust and gas that are actively collapsing to form new stars. We can see the swirling, flattened protoplanetary disks around hundreds of young stars, where dust grains are colliding and sticking together, right at this very moment, building the next generation of planets. The Orion Nebula doesn't just suggest the story of stardust reentry, it screams it. It demonstrates with vivid clarity that the beautiful, complex structures we see are made possible by the constant recycling of material from long-dead stars. Every new star being born there, every planet beginning to coalesce in those dusty disks, is direct proof that we are all truly made from the ashes of ancient giants. Now let's talk about time, because the journey of stardust isn't measured in years or centuries, but in epochs that stretch the very limits of human comprehension. We've followed this incredible voyage from a star's explosive death to its quiet rebirth in a new nursery. But to truly appreciate the scale of this cycle, we need to grapple with the immense timelines involved. This isn't a quick trip across town. It's a cross-galactic pilgrimage that can take longer than the entire existence of our species. The duration of this journey is anything but fixed. It's a sprawling tapestry of time, woven from the threads of distance, velocity, and the grand, slow-motion dance of the galaxy itself. Consider the first leg of the trip, the initial ejection and the long drift through interstellar space. If a supernova explodes relatively close to a star-forming region, say, within a few hundred light-years, the journey for its dust could be surprisingly quick on a cosmic scale. Propelled by the unimaginable force of the blast, these particles can be shot out at a significant fraction of the speed of light. In this best-case scenario, the dust could make it to a waiting nebula in a mere few 100,000 years. That might still sound like an eternity to us, but to the universe, it's a brief commute. However, this is the exception, not the rule. For stardust originating from older stellar populations in the distant reaches of the galaxy, or from stars that died long before any nearby nursery even began to form, the voyage is a different story entirely. This dust can wander aimlessly for hundreds of millions, even billions of years, caught in the gentle currents of the interstellar medium, its path slowly altered by the subtle gravitational tugs of passing stars and dark matter halos. It is a lonely, epic voyage where a single grain might circumnavigate the Milky Way multiple times before finally being drawn into a gravitational eddy that signals home. Once our stardust finally arrives at the outskirts of a molecular cloud, the clock resets for an entirely new process, the construction phase. This is no longer about travel, but about transformation. The initial collapse of a dense core within the nebula, triggered by that incoming shockwave or gravitational nudge, is itself a patient affair, taking on the order of 100,000 years. But that's just to get the protostar started. For a star like our Sun to fully form and ignite sustained fusion, clearing away the leftover gas and dust in its immediate vicinity, we're looking at a process spanning 1 to 10 million years. And the formation of planets from that swirling disk of debris, that adds another 1 to 10 million years onto the timeline. So, from the moment the stardust enters the nursery to the moment it becomes part of a finished planet orbiting a stable star, we are easily talking about 10 million years on the short end, and up to 100 million years for more massive, complex systems. This is a multi-generational construction project where the foremen are the laws of physics, and the only labor is gravity and time. This mind-bending timeline carries a profoundly beautiful implication. The stardust we are studying today, the grains found in meteorites, the particles detected by the James Webb Space Telescope in distant nebulae, is not a contemporary artifact. It is ancient history. The iron in your blood, the oxygen in your lungs, the calcium in your bones, many of these atoms were forged in stars that died and scattered their remains across the galaxy long before our Sun was even a glimmer in a nebula's eye. We are walking museums carrying within us the physical remnants of cosmic events that occurred 4.5, 5, even 6 billion years ago. When we look at a star-forming region like Orion, we are not just seeing the future, we are witnessing the culmination of a story that began in the deep past. The light we see from those stars left 1,000 years ago, but the dust we detect within that light is billions of years old, a relic from a bygone stellar era finally fulfilling its destiny. It connects us not just to the universe around us, but to the universe as it was, a living thread weaving through the vast expanse of cosmic time. This incredible story of cosmic recycling isn't just a theory we observe in distant nebulae. It's written into the very fabric of our own solar system, and we hold the proof right here on Earth. The evidence comes to us in the form of rare and ancient space rocks that have survived the fiery plunge through our atmosphere, meteorites. Not all meteorites are created equal, however. While most are fragments of asteroids or Mars, a special class known as carbonaceous chondrites are like time capsules, the most pristine and primitive remnants of the early solar system. And within these cosmic treasures, scientists have discovered something truly extraordinary: tiny, resilient grains of stardust that are actually older than our Sun itself. The most famous of these meteorites are the Murchison, which fell in Australia in 1969, and the Allende, which fell in Mexico that same year. When researchers began to painstakingly analyze these rocks, dissolving them in strong acids that ate away the more common solar system material, they were left with a tiny residue of something utterly alien. These are presolar grains, microscopic diamonds, graphite, silicon carbide, and other minerals that did not form in the cloud that gave birth to our sun and planets. They are the surviving seeds of other long-dead stars, and they carry a secret locked within their atomic structure, a chemical fingerprint that reveals their true, ancient origins. The key to unlocking this secret lies in the precise composition of these grains, specifically in their isotopic ratios. Think of an element like oxygen. Nearly all the oxygen on Earth is oxygen-16, meaning its atoms have 8 protons and 8 neutrons. But sometimes an oxygen atom will have 9 or 10 neutrons, making it oxygen-17 or oxygen-18. These different versions are called isotopes. Here's the crucial part: the specific ratio of these isotopes, how much oxygen-17 there is compared to oxygen-16, is like a signature. The nuclear fusion processes inside different types of stars, red giants, supernova, asymptotic giant branch stars, create wildly different and highly unusual isotopic ratios that are nothing like the average mix found in our solar system. When scientists find a microscopic grain of silicon carbide from the Murchison meteorite that has an isotopic ratio of carbon or silicon that is completely off the charts, they know with certainty that this grain could not have formed in our solar nebula. It is a literal piece of a different star, a tiny fragment of stardust that was drifting through the galaxy for billions of years before being swept up by the collapsing cloud that became our solar system. This means that when our solar system began to coalesce 4.5 billion years ago, it was not made from pure, virgin gas. It was a recycling bin, a mixture of material that had been enriched by generations of previous stars. These presolar grains were there, floating in the protoplanetary disk around our infant sun. They were incorporated into everything that formed from that disk. They are in the asteroids that orbit between Mars and Jupiter, in the comets that swing in from the frozen depths of the Oort cloud, and most importantly, they are in the planets. The Earth, and every one of us walking on it, contains atoms that were forged in the hearts of those distant, ancient suns. The calcium in your bones, the iron in your blood that carries oxygen to your cells, the carbon that forms the backbone of your DNA, all of it was once stardust, part of that incredible cycle of death and rebirth that we've been tracing. This transforms the entire concept from a beautiful astronomical abstraction into a deeply personal and physical connection. You are not just living on a planet, you are a walking collection of cosmic artifacts. You carry within you the legacy of stars that lived and died billions of years before our sun was born. Every breath you take draws in atoms that were fused in a supernova explosion. Every time your heart beats, it pumps blood that is enriched with elements created in the final moments of a red giant star. This isn't poetry or metaphor. It is the hard, empirical conclusion of modern astrophysics and geochemistry. The story of Stardust re-entering its birthplace is not just happening out there in the Orion Nebula. It is the story of our own origin. We are the universe having become aware of itself, and we are beginning to trace our own family tree back to the stars. Now, let's bring this cosmic story down to a more tangible scale, the birth of planets themselves. The arrival of Stardust into a stellar nursery isn't just a passive delivery of materials. It's an active, defining moment that sets the blueprint for entire solar systems. Think of a protoplanetary disk, that vast, swirling whirlpool of gas and dust around a young star, as a construction site. The gas is like the atmosphere of the site, necessary but formless. The stardust, however, is the actual lumber, steel, bricks, and wiring. It is the physical substance from which everything solid will be built, and its properties determine not only what gets built, but also the very architectural style of the final structures. The first and most fundamental role of these dust grains is to act as nucleation sites. In the cold, dense regions of the disk, gases like water, methane, and ammonia freeze directly onto the surfaces of these microscopic specks, forming thick, icy mantles. For rock formation, silicate dust grains constantly collide with each other. In the vacuum of space, there's no oxygen to create a layer of rust or tarnish, so their surfaces are chemically pristine and incredibly sticky at a molecular level. These gentle collisions cause them to cling together, growing from microscopic particles to millimeter-sized chondrules, then to centimeter-sized pebbles. This process, known as accretion, is the very first step in going from dust to a planet. Without these solid seeds, the gases in the disk would have nothing to condense onto, and planet formation might never even begin. The stardust provides the essential anchor, the foundation upon which worlds are slowly, painstakingly assembled, one microscopic collision at a time. But it's not just about providing bulk. The specific type of stardust is what writes the recipe for a planet's chemistry. Imagine two different deliveries arriving at that construction site. One truck is filled with carbon-rich dust, perhaps from the outflow of a Wolf-Rayet star or an asymptotic giant branch star. This carbon dust would lead to the formation of graphite, carbides, and a plethora of complex organic molecules. A planetary system forming from this material might be rich in dark, carbonaceous asteroids and could potentially give rise to planets with thick, hazy atmospheres and surfaces covered in tarry organic compounds. Now imagine another delivery, this one filled with dust rich in silicon, oxygen, and metals like magnesium and iron, dust typical of a supernova. This silicate-heavy dust is the recipe for rocks. It will form the basis for asteroids, rocky moons, and terrestrial planets like our own Earth, Mercury, Venus, and Mars. The very nature of the ground beneath your feet, whether it would be silicon-based rock or something far more exotic, was determined billions of years ago by the type of star that died and donated its dust to our solar nebula. Beyond the basic ingredients, the timing and quantity of this dust delivery act as a master regulator for the entire planetary construction project. A protoplanetary disk doesn't receive its stardust all at once. It's a continuous influx over hundreds of thousands of years. A massive early delivery of dust right as the disk is forming could create a huge number of initial nucleation sites, leading to the rapid formation of many planetesimals. This could result in a crowded inner solar system with many rocky worlds, perhaps leading to more collisions and a violent early history. Conversely, a slower, more gradual trickle of dust might result in fewer but larger planetary embryos. The amount of available solid material also directly influences the ultimate size of the planets. A rich vein of metallic dust injected into the inner disk could lead to the formation of a planet with an unusually large and dense metallic core, profoundly affecting its magnetic field and geological activity for billions of years. This variable delivery system helps explain the incredible diversity of exoplanets we've discovered, from diamond worlds to lava planets to super-Earths. It shows that the chaos of stellar death doesn't just provide the materials, it also provides the instructions, written in the language of timing and quantity, that dictate the final architecture of a solar system. Therefore, the humble grain of stardust is so much more than a relic. It is a blueprint, a building block, and a chemical catalyst all in one. Its journey across light years culminates in its most important role, determining the character of new worlds. The variety of planets we see across the galaxy, the rocky spheres, the gas giants, the ice worlds, is a direct reflection of the variety of stars that came before and the unique blend of stardust they contributed. Our own solar system, with its ringed gas giants, its belt of asteroids, and its single vibrant rocky world teeming with life, is the direct product of a specific recipe of stardust delivered at a specific time from specific types of long-dead stars. We are not just living in a solar system, we are living in the finished product of this grand cosmic recycling program, a testament to the enduring legacy of Stardust. But the journey of Stardust doesn't end with the formation of planets. In many ways, that's where its most profound role truly begins. We've seen how these tiny grains act as the building blocks for worlds, but they also carry something far more precious within them, the very ingredients for life itself. This isn't just about carbon and oxygen anymore. We're talking about complex organic molecules, the kind that form the foundation of every living thing on Earth. And the incredible part is that these biological building blocks aren't necessarily created on planets. They are often forged in the cold, dark depths of space, right on the surfaces of these wandering dust grains, long before a planet even exists. Inside the protective cocoon of a nebula, shielded from the harshest radiation but still bathed in the gentle glow of forming stars, a quiet kind of chemistry is taking place on every available surface. Remember those icy mantles that form on stardust grains? They become miniature laboratories. Simple molecules like water, carbon monoxide, ammonia, and methane freeze onto these specks, creating a frozen matrix. Then the ultraviolet radiation from nearby young stars, which seems so destructive, actually provides the spark of creation. This high-energy light breaks apart the simple molecules, creating a soup of highly reactive fragments, ions, and radicals that are desperate to form new bonds. Trapped together on the tiny, cold stage of the dust grain, these fragments randomly reconnect, but now in new, more complex arrangements. Through this process, known as photochemistry, the simple becomes complex. From basic ices, the nebula can produce ethanol, formaldehyde, and even the simplest amino acids like glycine. These are not living things, not by any stretch, but they are the fundamental Lego bricks from which the structures of life can eventually be assembled. This organically rich stardust doesn't just stay out in the nebula, it gets incorporated directly into the next generation of celestial bodies. As the protoplanetary disk swirls around a new star, this dust, now coated in a layer of complex organic material, begins to clump together. It forms part of the asteroids and comets that will eventually make up the outer reaches of the young solar system. Then, in a dramatic delivery event, these icy bodies become the couriers of life's potential. In the early, violent days of a solar system, the inner planets are subjected to a constant barrage of impacts from comets and asteroids. This period, known as the Late Heavy Bombardment, was once thought to be purely destructive. But we now understand it had a creative side. Each comet that slammed into the early Earth was essentially a cargo ship from the outer solar system, delivering vast quantities of water and, crucially, these pre-formed organic molecules. They were literally raining down from the sky, seeding our planet with the chemical precursors necessary for biology to emerge. The evidence for this isn't just theoretical. We've found amino acids in meteorites like the Murchison meteorite, which fell to Earth in 1969. Analysis of this rock revealed over 90 different amino acids, many of which are used by life on Earth today, while others are not. Clear proof that these compounds can form naturally through non-biological processes in space. Furthermore, space missions like NASA's Stardust mission, which collected particles from the tail of Comet Wild 2, and the Rosetta mission, which studied Comet 67P, both detected a range of organic molecules, including the amino acid glycine, right there in the comet's nucleus. These missions provide direct, incontrovertible evidence that the building blocks of life are not unique to Earth. They are a common product of cosmic chemistry, manufactured on dust grains and distributed throughout solar systems by comets and asteroids. This changes everything about how we view our place in the universe. The emergence of life on Earth may not have been a bizarre, isolated chemical fluke that started from absolute scratch in a primordial pond. Instead, it might have been a process that was given a massive head start. The universe, through its endless cycle of star death and rebirth, had already done much of the hard work. It forged the heavy elements in stellar furnaces. It assembled them into complex organic molecules on the surfaces of stardust in nebulae, and it then delivered this pre-made chemical toolkit to our planet via cometary impacts. This doesn't answer the question of how inert chemistry transitioned into living biology. That magnificent leap is still one of science's greatest mysteries, but it powerfully suggests that the raw materials for life are a natural and widespread consequence of astrophysical processes. The cosmic cycle of stardust, therefore, does more than just build new worlds. It pre-stocks them with the essential ingredients, making the universe potentially far more fertile and filled with possibility than we ever dared to imagine. While the gentle winds of sun-like stars create beautiful planetary nebulae, it is the titanic, explosive deaths of the most massive stars that serve as the universe's primary foundries for stardust. These supernovae are not merely an end, they are a spectacular, violent rebirth, an event of such immense power that it forges the heaviest elements and blasts them outward, where they can rapidly condense into vast clouds of new dust. The sheer quantity of material these events produce is almost incomprehensible. A single supernova can generate enough stardust to outweigh our entire planet Earth thousands of times over, ejecting it at nearly a tenth the speed of light. This isn't a slow, gentle puff of material. It's a cosmic shotgun blast, spraying the surrounding interstellar medium with a rich, heavy element-laden payload that is absolutely essential for building rocky planets and the chemistry of life. We can actually witness this incredible process unfolding in real time by studying supernova remnants. Take Cassiopeia A, the expanding cloud of debris from a star that exploded about 350 years ago. When astronomers point powerful infrared telescopes like the Spitzer Space Telescope and the James Webb Space Telescope at this chaotic region, they don't just see hot gas. They see something astonishing, the heat signature of countless trillions of newly formed dust grains. In the years immediately following the explosion, the expanding ejecta is far too hot for solids to form. But as this material races outward, it rapidly expands and cools. Once the temperature drops below a certain point, atoms of silicon, iron, oxygen, and carbon suddenly begin to stick together, nucleating into tiny solid particles right there in the void. It's like watching steam from a kettle condense into water droplets on a cold window, but on a cosmic scale and with elements forged in a stellar inferno. Observations show that this dust formation can happen remarkably quickly, within just a few hundred years of the star's death, creating an expanding shell of pristine stardust that will eventually mix with the wider galaxy. The recipe for this dust is written in the extreme physics of the explosion itself. The incredible pressure and temperature inside the collapsing core of a massive star are the only places in the universe violent enough to create elements heavier than iron through a process called rapid neutron capture. This is how we get elements like gold, silver, platinum, and uranium. But the supernova is also a prolific producer of more common, yet equally vital elements. Enormous quantities of silicon and oxygen are forged, which will later condense into silicate grains, the basic stuff of rocks and sand. Carbon atoms are created in abundance, ready to form graphite and diamond dust. Iron and nickel are synthesized, providing the metallic cores for future asteroids and planetary cores. The supernova doesn't just make the dust, it manufactures every single ingredient from scratch, cooking them in its unimaginable fire and then packaging them for delivery. And the delivery service is incredibly efficient. The supernova doesn't just create this dust and leave it sitting in one place. Its shockwave acts as a powerful dispersal mechanism, ensuring the new material is thoroughly mixed into nearby regions of gas. This is where the story becomes a beautiful cycle of destruction begetting creation. The same powerful shockwave that tears the star apart and blasts its dust into space will eventually slam into a nearby, relatively peaceful molecular cloud. This collision is like a cosmic snowplow, violently compressing the cloud's gas and dust. This compression does two critical things. First, it triggers gravitational collapse in the cloud, initiating the birth of a new generation of stars. Second, it injects the cloud with that freshly made supernova dust, enriching it with the heavy elements necessary to form terrestrial planets. The death of one star, therefore, directly catalyzes the birth of many others and provides them with the planetary building blocks right from the very start. This makes supernova indispensable architects of the universe as we know it. Without these periodic, catastrophic explosions, the cosmos would be a very different and far less interesting place. The interstellar medium would consist almost entirely of the primordial hydrogen and helium from the Big Bang. There would be no silicon for rocks, no oxygen for water, no carbon for organic molecules, and no iron for planetary cores. The universe would be devoid of rocky planets, filled instead with gas giants and failed stars. There would be no Earth, no continents, no oceans, and certainly no life. Every time we see the brief, brilliant flash of a supernova in a distant galaxy, we are witnessing the most powerful engine of material renewal in the cosmos. It is a violent, necessary death that seeds the galaxy with the potential for new worlds and new possibilities, ensuring that the story of the universe is one of ever-increasing complexity and wonder. Yet for all its resilience, this cosmic journey is fraught with peril, and a staggering amount of stardust never completes its voyage home. The path back to a stellar nursery is a veritable gauntlet of destruction, where countless grains are vaporized, shattered, or simply eroded away into nothingness long before they can contribute to a new generation of stars and planets. This relentless process of dust destruction is a critical counterbalance to creation, a reminder that the universe is not only a builder but also a demolisher, and that the cosmic recycling program operates with immense efficiency but also with staggering waste. One of the most immediate and violent threats comes from the very events that create the dust in the first place, supernova. While these titanic explosions are prolific dust factories, their own shockwaves can be incredibly destructive. Imagine a newly formed grain of silicate, freshly condensed from the expanding ejecta of a supernova. Just as it begins its life, it is overtaken by the reverse shock, a rebound effect from the explosion slamming into slower-moving material or the surrounding interstellar medium. This shockwave, traveling at millions of kilometers per hour, can subject the fragile dust grain to such intense heat and pressure that it is instantly vaporized, turning it back into a gaseous state before it ever gets a chance to leave its birthplace. It's a cruel cosmic irony. The same event that gives it life can also immediately snuff it out. Beyond the chaotic aftermath of its own birth, Stardust faces constant danger from the most luminous objects in the galaxy, massive hot stars. Drifting too close to an O-type star or a Wolf-Rayet star is a death sentence for a dust grain. These stellar behemoths flood their surroundings with intense ultraviolet radiation and powerful stellar winds. The UV radiation heats the dust to sublimation points, causing it to transition directly from a solid back into a gas without even becoming a liquid. Meanwhile, the relentless torrent of particles in the stellar wind acts like a perpetual sandblaster, relentlessly scouring the surfaces of dust grains and chipping them away atom by atom in a process known as sputtering. This is why we often see beautiful, hollowed-out bubbles and cavities in nebulae like NGC 339. The central stars have effectively cleared out a vast region around themselves, vaporizing or blowing away all the dust that once resided there. Even in the quiet, dark stretches of interstellar space, far from any obvious immediate threat, the destruction continues at a slower, more insidious pace. Cosmic rays' atomic nuclei accelerated to nearly the speed of light by distant supernova and black holes constantly pepper every cubic centimeter of space. A direct hit from one of these high-energy particles can blast a chunk right out of a dust grain or even shatter it into pieces. Over millions of years, this relentless bombardment can slowly erode a large grain down to nothing or fatally damage its crystalline structure. Furthermore, the gentle but persistent drag force experienced as a grain moves through the thin interstellar gas can cause collisions with other atoms. While these bumps are minor, over astronomical timescales, they contribute to a gradual sanding down effect, wearing the grain away. Finally, even if a particle of stardust miraculously survives all these hazards and successfully arrives in a new planetary system, its journey might still end in oblivion. As it spirals into the protoplanetary disk around a young star, it faces new risks. It could be drawn by gravity inward toward the fiery embrace of the central star itself, where it would be instantly vaporized and assimilated. Alternatively, its path might be altered by the gravitational pull of a newly formed gas giant, flinging it out of the system entirely and condemning it to an eternal, frigid exile in the lonely intergalactic void. The fact that any stardust survives this epic, billion-year obstacle course at all is a testament to its tenacity. This delicate balance between creation and destruction ensures that while the universe is constantly enriched, it is never overwhelmed, maintaining a cycle of renewal that is both brutally efficient and beautifully fragile. The quest to understand stardust has moved from the realm of theoretical astronomy into a hands-on, experimental science, all thanks to a suite of technological marvels that act as our time machines and microscopes for the cosmos. We are no longer limited to just observing these particles from a mind-boggling distance. We can now chase them down, capture them, and bring pieces of them back to Earth for intimate study. This revolution in capability has transformed dusty, theoretical models into a clear, empirical picture of our cosmic ancestry, and it's being driven by missions, telescopes, and lab instruments that push the very boundaries of engineering and physics. Perhaps the most audacious effort to grab a piece of this cosmic history was NASA's aptly named Stardust mission. Launched in 1999, its goal was almost science fiction: to rendezvous with a comet, fly through its tail, and capture particles of its dust without destroying them. Comets like Wild 2 are considered icy time capsules, preserved since the formation of the solar system, and they were thought to be loaded with ancient stardust. The spacecraft was equipped with a collector tray filled with a substance called aerogel, an ethereal, bluish material that is 99.8% air. This miraculous substance is like a ghostly net. It has the density of smoke, allowing it to gently slow down and capture hypervelocity dust particles without vaporizing them, preserving them in a state of near-pristine suspension. When Stardust returned to Earth in 2006, scientists found their treasure trove. Tucked within the aerogel were tiny particles. An analysis confirmed that many were indeed presolar grain stardust that predated our Sun, exactly as predicted. This wasn't just remote sensing. This was like an interplanetary archaeologist bringing back a piece of the cathedral that built our solar system. While Stardust went out to collect samples, a new generation of telescopes began to see the universe in entirely new light, quite literally. The James Webb Space Telescope, with its massive golden mirror and suite of incredibly sensitive infrared instruments, has become our premier window into the dusty hearts of stellar nurseries. Where visible light telescopes see only dark, obscuring clouds, Webb's infrared eyes peer right through the veil. It doesn't see darkness, it sees the heat signature of every dust grain, mapping their temperature and distribution with stunning precision. A single image from Webb, like that of the pillars of creation, is more than a beautiful poster, it's a detailed data set. We can see which regions are dense with accumulating dust, where radiation from new stars is evaporating material away, and even identify the chemical fingerprints of ices and complex molecules frozen onto those grains. It provides a real-time, panoramic view of the cosmic recycling process in action, showing us not just where stardust is, but what it's doing and what it's becoming. Back on Earth, the science shifts from the panoramic to the profoundly microscopic. The particles collected by stardust or found in primitive meteorites are vanishingly small, often smaller than a single human cell. Analyzing them requires instruments of incredible precision. The workhorse here is a device called a secondary ion mass spectrometer, or SIMS. This machine operates like a cosmic sleuth's magnifying glass. It focuses a beam of ions onto a tiny grain, blasting atoms from its surface. These atoms are then funneled into a mass spectrometer, which sorts them by weight, allowing scientists to count individual atoms of different isotopes. This is how we read the grain's unique passport stamp. Finding an overabundance of certain isotopes, like silicon-30, or a specific ratio of carbon-12 to carbon-13, is the definitive proof that this grain formed in a specific type of star, a red giant, a supernova, or a Wolf-Rayet star. This isn't guesswork, it's forensic-level evidence that places a piece of stellar debris at the scene of its own creation, billions of years ago and countless light years away. Finally, weaving all this observational and laboratory data together are sophisticated computational models. These are complex simulations run on some of the world's most powerful supercomputers, designed to recreate the life of a dust grain. They account for the gentle push of radiation pressure, the subtle tugs of gravity from passing stars and dark matter, the erosive effects of cosmic rays, and the dynamics of a grain tumbling through a turbulent nebula. By inputting the known physics, scientists can run these simulations backwards to trace the likely journey of a grain found in a meteorite, or forwards to predict how dust will behave in a protoplanetary disk. These digital laboratories allow us to test theories and understand processes we could never directly observe, filling in the gaps between the snapshots provided by telescopes and the hard evidence from our labs. Together, this technological trinity, sample return, advanced telescopes, and hypersensitive lab analysis has given us a complete toolkit to dismantle the mystery of stardust, transforming a poetic notion into a precise and deeply personal chapter in the story of our universe. This grand cycle of stardust is perhaps the most profound example of cosmic recycling we know of. It's a universal process of renewal that ensures nothing in the universe is ever truly wasted. The iron in your blood, the oxygen in your lungs, the calcium in your bones, these atoms are not new. They have been on an epic journey for billions of years, used and reused in an endless loop of creation and destruction. When a massive star ends its life in a supernova, it isn't just vanishing. It is scattering its essence across the galaxy, enriching vast clouds of gas and dust with the heavy elements necessary for rocky planets and living things. That material then gets drawn into new stellar nurseries, where gravity pulls it together to form the next generation of stars and planets. This isn't a one-time event. It's a continuous, self-sustaining cycle that has been running since the first stars lit up the cosmos, each generation building on the ashes of the last, making the universe increasingly complex and fertile over time. This concept mirrors the most fundamental cycles we see here on Earth, but on a truly galactic scale. Think about the water cycle. A molecule of water evaporates from the ocean, forms a cloud, rains down on a mountain, flows into a river, and eventually returns to the sea, only to begin the process again. Or consider the carbon cycle, where a carbon atom moves from the atmosphere into a plant, then into an animal that eats the plant, and back into the soil after it dies, where it can be taken up by another plant. These are cycles of conservation and transformation, where matter is never created or destroyed, but is constantly repurposed into new forms. The cosmic dust cycle is the exact same principle, but instead of water or carbon moving between the land, sea, and sky, its entire elements moving between stars, nebulae, and planets across light years of space. The universe, in its own magnificent way, is practicing the ultimate form of sustainability. This relentless recycling is the primary engine driving the evolution of galaxies. In the early universe after the Big Bang, there were only the lightest elements, hydrogen, helium, and a trace amount of lithium. There was no carbon, no oxygen, no iron, none of the ingredients needed for planets or life. The first generation of stars had to make do with this sparse pantry, but when those first massive stars died, they filled the cosmos with new, heavier elements. The second generation of stars formed from this enriched material, and when they died, they contributed an even richer mix of elements. With each successive cycle, the galaxies became more and more chemically complex. This enrichment is what allowed for the formation of not just stars, but rocky planets, moons, asteroids, and comets. Without this ongoing process of stellar death and rebirth, our Milky Way would still be a bland soup of hydrogen gas, devoid of the variety and complexity that makes our existence possible. Grasping this immense cycle fundamentally changes our perspective on our place in the cosmos. We are not separate from the universe, looking in from the outside. We are a product of it, woven into its very fabric. The atoms that make up our bodies were forged in the hearts of long-dead stars, scattered across space by their violent deaths, and then carefully assembled into our planet and into us. We are not just observers of the cosmic dance, we are active participants. Every breath you take draws in atoms that were once part of a red giant star. Every beat of your heart is powered by energy from the sun, a star whose material was recycled from countless previous generations. We are the universe become conscious, a way for the cosmos to look back on itself and understand its own history and its own incredible story of transformation. This knowledge connects us to everything we see in the night sky, not as distant, unrelated points of light, but as relatives in a vast, interconnected family tree that stretches across space and time. Despite the rock-solid science behind it, the idea of stardust often gets wrapped in a layer of beautiful but ultimately misleading mythology. Perhaps the most common misconception is that when we say, "we are made of stardust," it's merely a poetic metaphor, a lovely turn of phrase to express our connection to the cosmos, but not a literal, physical truth. In reality, it is a direct chemical fact. The atoms that constitute our bodies, the iron in our blood, the calcium in our bones, the oxygen we breathe, were not present in the universe immediately after the Big Bang. They were forged in the nuclear furnaces of stars and scattered across the galaxy by their explosive deaths. This isn't philosophy. It's astrophysics and chemistry confirmed by analyzing the isotopic signatures in meteorites. We are quite literally assembled from material that was once part of other celestial bodies. This leads directly to a second, related myth: the idea that stardust is somehow magical or that it possesses a mystical life-giving property, transforming directly from an inert cosmic speck into a living cell. The truth is far more fascinating and complex. Stardust itself is not alive, nor does it magically become life. Its role is that of a supplier and a delivery vehicle. It provides the essential raw materials, the carbon, nitrogen, oxygen, and other elements, and, as we've seen, it can act as a template for forming complex organic molecules like amino acids in the cold of space. But the leap from those organic building blocks to a self-replicating living organism is a separate, intricate process of chemistry and evolution that happens on planets, not in the void. Stardust sets the table with an incredibly rich feast of ingredients, but it doesn't prepare the meal. Understanding this distinction doesn't diminish the wonder, it enhances it. The miracle isn't magic. It's the incredible series of natural, physical processes that can take atoms from a supernova and, over billions of years and through countless steps, arrange them into a thinking, feeling being capable of wondering about its own origins. Another surprising misconception is that stardust is a rare and precious substance, perhaps something we might find in a tiny, glittering vial if we could only travel to the right star. In fact, the opposite is true. Stardust is one of the most common solid materials in the universe. It is ubiquitous. It fills the immense spaces between the stars, not as a thin, ethereal haze, but as a pervasive fog of microscopic particles. Those dark, blank patches you see when you look at the Milky Way, those aren't empty voids. They are dense, towering clouds of gas and dust, blocking the light from the stars behind them. Every single galaxy is suffused with it. Our own solar system is constantly plowing through this interstellar medium, sweeping up dust as we orbit the galactic center. It is so common that on a clear, dark night, you are likely breathing in a few atoms of stardust that drifted into Earth's atmosphere. Its abundance is precisely what makes the cosmic cycle possible. If it were rare, there wouldn't be nearly enough material to build successive generations of stars and planets. Clarifying these points is crucial because it grounds the profound poetry of the concept in the even more powerful bedrock of empirical science. The real story doesn't need embellishment or mysticism to be awe-inspiring. The fact that we can hold a piece of a star in a laboratory, that we can trace the journey of an atom across billions of years, and that we understand the intricate chemistry that turns stellar debris into the precursors of life, these are triumphs of human curiosity and reason. This knowledge allows us to replace a vague sense of wonder with a deep, evidence-based appreciation for our place in the cosmos. We are not just connected to the universe by a beautiful idea. We are physically woven into its history, its processes, and its future through the continuous, tangible cycle of stardust. Just as different factories produce different products, the type of star that creates stardust leaves an indelible mark on its composition, crafting a unique elemental signature that tells a story of its violent or gentle birth. This isn't a one-size-fits-all substance. It's a diverse family of materials, each with its own origin story and cosmic destiny. The final recipe of a dust grain depends almost entirely on the mass, age, and internal processes of its parent star, making each type of stellar death a specialized workshop for a particular kind of cosmic building block. Consider the humble, sun-like star, a main sequence star that will end its days not with a bang, but with a series of elegant, layered farewells. As such a star enters its red giant phase, its outer layers expand and cool, creating a perfect environment for dust formation right in its own atmosphere. Here, in these relatively calm and carbon-rich conditions, the most common products are grains of graphite pure carbon and silicon carbide. It's a slow, methodical process, like soot gently collecting inside a chimney flue. The stellar winds that eventually blow these layers away into a planetary nebula are therefore filled with this carbon-rich dust. This material is the universe's primary source of carbon, the fundamental atom for all organic chemistry, and it gets scattered into the galaxy in a beautiful, glowing shroud. Now contrast that with the spectacular end of a true stellar titan, a massive star that dies in a supernova explosion. The environment here couldn't be more different. It's a place of unimaginable violence, extreme temperatures, and insane pressures. In this cosmic cataclysm, the conditions are right to forge the very heaviest elements in the periodic table through rapid neutron capture. This is how we get elements like iron, nickel, zinc, and even silver, gold, and uranium. The dust that condenses from this expanding fireball is therefore incredibly metal-rich and diverse. You'll find grains of pure iron and nickel, and various silicates heavily laced with these metals. This supernova dust is the primary source of most of the heavy elements that make up the cores of rocky planets and the metals we use here on Earth. It's the difference between a gentle craftsman and an industrial smelter. Both create, but the products are fundamentally different. Then there are the truly exotic stellar dust factories like Wolf-Rayet stars. These are massive, incredibly hot stars that are literally peeling themselves apart with their own ferocious radiation pressure. They experience such powerful stellar winds that they blast their own outer layers into space at millions of kilometers per hour. Despite their intense heat, the outer regions of these winds can expand and cool rapidly enough for dust to actually form. And because Wolf-Rayet stars are often highly enriched in carbon due to internal nuclear processes brought to the surface, the dust they produce is exceptionally carbon-rich, often forming complex carbon molecules and even tiny nanodiamonds. This dust gets injected directly into the surrounding space at tremendous speeds, creating beautiful, expanding pinwheel-like structures that we can observe with telescopes. Another prolific producer is the asymptotic giant branch star, or a GB star. This is actually a late stage in the life of a low to medium mass star, even more evolved than the red giant phase. These stars are like cosmic chemical factories with a pulsating heart. They undergo thermal pulses, which dredge up newly synthesized material from their deep interiors to the surface. This material includes not just carbon, but also elements like oxygen and sulfur, which were created through helium fusion. Depending on the exact ratio of carbon to oxygen in their atmospheres, a GB stars can produce either carbon-rich dust like graphite or oxygen-rich dust, which condenses into various types of silicate grains, as well as oxides and sulfides like alumina and silicon monoxide. Their slow, steady winds make them one of the most significant contributors of new dust to the interstellar medium in galaxies like our Milky Way. This incredible diversity in stardust has a direct and profound impact on the kind of planetary systems that can form. A protoplanetary disk enriched with carbon-rich dust from Wolf-Rayet stars or carbon-rich GB stars might give rise to a very different kind of planetology. We could see worlds with graphite crusts, mountains of diamond, or atmospheres thick with complex, hazy hydrocarbons. In contrast, a system seeded predominantly with silicate and metal-rich dust from supernova would be much more likely to form rocky, metallic planets like our own Earth, with a solid silicate mantle and a dense iron-nickel core. The initial chemical inventory delivered by the Stardust essentially sets the entire menu for planet formation. It determines a world's fundamental geology, the composition of its atmosphere, and even its potential to host the chemistry of life. This variation is a key reason why the thousands of exoplanets we've discovered exhibit such a stunning array of properties. They were all built from slightly different blends of cosmic ingredients, each batch bearing the unique signature of the stars that came before. While our understanding of the cosmic dust cycle has grown immensely, some of the most thrilling questions are only now coming into focus, driving a new wave of research that will fundamentally reshape our view of the universe's history and its potential for life. Future investigations are set to push into three particularly fascinating frontiers: the very origins of dust in the infant universe, its role in shaping alien worlds light years away, and its potential to carry the signatures of biology across the galaxy. Each of these paths requires a new generation of technology, both on Earth and in space, designed to peel back layers of the cosmos we've only begun to glimpse. One of the most profound mysteries is how this entire cycle began. After the Big Bang, the universe contained only hydrogen, helium, and a tiny bit of lithium. There were no heavy elements, and therefore no dust. The first stars, known as population 3 stars, are thought to have been colossal, short-lived behemoths. When they died in supernova, they would have created the very first grains of stardust, seeding the pristine cosmos for the very first time. But we have never directly observed these first stars or the dust they produced. Upcoming observatories like the NASA and Nancy Grace Roman Space Telescope and the European Extremely Large Telescope will peer back to these cosmic dawn epochs, not to see the stars themselves, but to detect the telltale shadow of their dust. They will look for the specific way this primordial dust dims and reddens the light from the most distant quasars, acting as a forensic clue to its composition and quantity. Understanding this first dust is crucial, as it would have catalyzed the formation of the second generation of stars and the first galaxies, setting the entire cosmic recycling program in motion billions of years ago. Closer to home, in a sense, the study of exoplanets is entering a new, dust-focused era. We've discovered thousands of worlds around other stars, but now we want to understand their atmospheres and surfaces. Here, stardust plays a dual role. First, it is the primary source of the cloud particles and haze that shroud many exoplanets. Missions like the ESA's Ariel Space Telescope, scheduled for launch in 2029, are specifically designed to perform spectroscopy on the atmospheres of hundreds of exoplanets. By analyzing the starlight filtering through these alien skies, Ariel will detect the chemical fingerprints of silicate clouds, graphite haze, and other aerosol particles that originated as stardust. This will tell us not just what a planet's atmosphere is made of, but what the weather is like, whether it has raining gems or clouds of glass. Secondly, by studying the composition of these dust-borne aerosols, we can indirectly measure the specific blend of stardust that formed that planetary system, working backwards to understand the types of stars that died to create it. It's a way of doing galactic archaeology from light years away, using a planet's atmosphere as a historical record. Perhaps the most tantalizing direction for future research lies in the hunt for biosignatures not on planets, but on the dust grains themselves. We now know that complex organic molecules, including amino acids, can form on icy dust grains in nebulae. The next step is to determine just how complex this chemistry can become. Advanced laboratory experiments are now simulating the conditions of protoplanetary disks with incredible accuracy, zapping icy mixtures with UV radiation and subjecting them to pressure changes to see if they can produce molecules like nucleotides, the building blocks of RNA and DNA. In parallel, astronomers are developing the tools to one day detect these molecules in space. This wouldn't be looking for life itself, but for its potential, a concept known as a prebiotic signature. If we can find evidence that the basic informational molecules of life are being manufactured in abundance on dust grains throughout the galaxy, it would powerfully suggest that the ingredients for biology are a universal and common outcome of astrophysical processes, dramatically increasing the odds that life itself is widespread. To achieve these ambitious goals, scientists are not relying on a single method, but are building a powerful triad of investigative tools. Space missions like Ariel and the James Webb Space Telescope will continue to provide observational data from the cosmos. Here on Earth, sophisticated laboratory astrophysics experiments will recreate the cold vacuum of space in chambers, bombarding ices with radiation to watch chemistry unfold in real time. And finally, supercomputer simulations are becoming so advanced that they can now track the life of a single dust grain, from its condensation in a stellar wind, through its journey across interstellar space, to its final accretion into a comet in a young solar system. These models incorporate radiation pressure, magnetic fields, and galactic gravity to predict the paths of dust, allowing us to virtually trace our own cosmic ancestry. The ultimate questions these efforts seek to answer are as grand as they are fundamental. How much stardust is the cosmic minimum required to trigger the collapse of a gas cloud and kickstart star formation? Is there a threshold that separates a sterile universe from one brimming with stars and planets? And just how common is dust that is organically rich, pre-loaded with the precursors for life? The answers will tell us whether our own existence is a miraculous cosmic fluke or an inevitable consequence of the laws of physics and chemistry playing out across a universe that is inherently fertile and creative. The next decade of research promises to transform stardust from a beautiful abstract concept into a quantifiable, tangible key for unlocking the history of everything, from the first stars to the potential for life on worlds we have yet to discover. This changes the entire framework of the search for extraterrestrial life, shifting it from a question of possibility to one of probability. For decades, the quest to find life beyond Earth was often framed by the famous Drake equation, which included variables we could only guess at. But now, with our understanding of the cosmic dust cycle, we can start to replace some of those question marks with hard data. We now know that the fundamental building blocks of life aren't rare, exotic commodities that must be painstakingly assembled from scratch on each individual planet. Instead, they are a universal, pre-packaged resource, manufactured in bulk in the chemical laboratories of Nebulae and delivered express to any emerging world within a star-forming region. This means that the raw ingredients for biology, the amino acids, the sugars, the lipids, are likely present on nearly every young, rocky planet that forms within the habitable zone of its star. The starting line for life, therefore, isn't at the beginning of a complex chemical synthesis. It's much further along the track, with a rich and varied organic toolkit already unlocked and waiting. This knowledge gives astronomers a powerful new strategy in the hunt for habitable worlds. Instead of just looking for planets that are roughly Earth-sized and orbiting within the so-called Goldilocks zone where liquid water can exist, we can now also look at the environment in which that planet was born. By using telescopes like the James Webb Space Telescope to study the protoplanetary disks around young stars, scientists can perform a kind of cosmic chemical prospecting. They can analyze the light from these disks to detect the spectroscopic fingerprints of complex organic molecules frozen onto dust grains. Finding a system with a particularly rich concentration of these probiotic molecules would immediately flag it as a high-priority target, a place where the conditions were not just right for life in terms of temperature and water, but also in terms of its chemical head start. It allows us to move beyond simply looking for Earth twins and start identifying worlds that might be even more primed for the emergence of biology than our own solar system was 4.5 billion years ago. The implications reach even further than identifying promising locations. The stardust itself could one day provide us with a direct detection of life, a concept known as a biosignature. Imagine a future where we can not only detect the atmosphere of a distant exoplanet, but also analyze the composition of the interstellar dust grains currently drifting into that solar system. If a grain were to pass through a biosphere, perhaps one with widespread microbial life or even complex vegetation, it could potentially pick up a hitchhiker. Certain molecules, like the distinctive chlorophyll that makes plants green on Earth, have a very specific and detectable spectroscopic signature. If such a molecule were to adhere to a dust grain, and that grain were then ejected from that solar system by gravitational forces to eventually travel across the galaxy, it could theoretically carry that signature with it. While this is a far-fetched scenario, it illustrates a profound shift in thinking. The signs of life might not be confined to the planets themselves. They could be encoded on the very motes of dust that travel between the stars, turning the entire interstellar medium into a potential library of biological information. This grand perspective fundamentally alters the odds in the search for life. The cosmic dust cycle is not a rare or special event. It is a continuous, ubiquitous process that operates in every galaxy, in every star-forming region, all across the universe. It is the universe's default setting for distributing the ingredients of complexity. Therefore, the emergence of life is not a bizarre, one in a trillion fluke that happened on one lucky planet. It becomes a natural and even expected outcome of astrophysics and chemistry, a process that the universe is hardwired to promote. The constant sowing of organic-laden stardust onto young worlds means that the potential for life is being tested everywhere all the time. While this doesn't guarantee that intelligent, technological civilizations are common, it strongly suggests that the initial spark of biology, the transition from complex chemistry to simple, replicating life, is likely a widespread phenomenon. It connects us to the cosmos not as lonely outliers, but as participants in a much larger, potentially living universe, where the same stardust that flows through our veins likely flows through the systems of countless other worlds, carrying with it the same profound potential. Beyond the telescope and the laboratory, the story of Stardust resonates on a level that is deeply, profoundly human. It has captivated our imagination for centuries, not just as a scientific concept, but as a powerful symbol that bridges the cold facts of astrophysics with the warm, searching questions of our own existence. Long before we had mass spectrometers to prove it, poets, artists, and philosophers looked up at the night sky and felt a connection, an intuition that we are not separate from the cosmos, but a part of it. This isn't a new idea born of modern science. It is an ancient recognition that has been expressed in 1,000 different ways across human culture, and it speaks to a universal yearning to understand our place in the grand scheme of things. Perhaps the most famous and eloquent expression of this idea comes from the astronomer Carl Sagan, who in his iconic television series Cosmos looked into the camera and told us, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies were made in the interiors of collapsing stars. We are made of star stuff." That single word, star stuff, did something remarkable. It took a complex astrophysical process and distilled it into a potent, beautiful, and instantly relatable concept. Sagan wasn't just stating a chemical fact. He was offering a new origin story for humanity itself, one that is both humbling and exalted. It tells us that we are not merely living on a planet, but that we are the planet and the stars made conscious. This blending of rigorous science with a sense of profound wonder is Sagan's enduring legacy, and it has inspired countless people to see the universe and themselves in an entirely new light. This theme of our cosmic connection echoes throughout the art and music of the modern era. From David Bowie's alter ego Ziggy Stardust, a rock and roll messiah from the stars, to the countless songs that use space and stardust as metaphors for love, loss, and transcendence, the idea is a fixture in our creative landscape. It appears in films and literature as a symbol of our greatest hopes and our most ancient mysteries. This cultural embrace isn't about the technical details of nucleosynthesis. It's about the emotional and spiritual weight of the idea. It provides a narrative that satisfies a deep human need to belong to something larger than ourselves, to see our individual stories as part of a much older, grander epic. If we look even further back to the wisdom traditions and philosophies of the world, we find that dust has always carried a dual symbolism. On one hand, it represents humility and impermanence. In many religious texts, the phrase, "ashes to ashes, dust to dust," is a poignant reminder of our mortality, that our physical forms are transient and will one day return to the earth. Yet simultaneously, dust holds a cosmic significance. In various creation myths, gods or divine beings form the first humans from the dust of the ground, breathing spirit into the material world. This is a powerful parallel to the scientific narrative. In both, we are fashioned from the raw material of the universe. We are both humble and magnificent, fleeting yet eternal in our constituent parts. The Stardust cycle gives a scientific backbone to this ancient philosophical paradox, showing us that we are indeed made from the dust of the earth, which was itself made from the dust of stars. This leads to a truly profound philosophical reflection on the nature of impermanence and renewal. The entire cosmic cycle is a lesson in transformation. Nothing is truly lost, it is only changed. A star dies a violent death, but that death gives birth to new worlds and new possibilities. The atoms in your body will one day be returned to the universe, perhaps to become part of a distant nebula, a new planet, or even another living being a billion years from now. This is not a morbid thought, but a liberating one. It echoes central tenets in many spiritual traditions, from the Buddhist concept of rebirth to the continuous cycles of creation and destruction in Hindu cosmology. It teaches us that endings are also beginnings, that decay feeds new growth, and that we are all participants in an endless, dynamic dance of matter and energy. Understanding this can foster a deep sense of peace and connection, alleviating the fear of isolation and reminding us that we are never truly separate from the flow of the cosmos around us. This rich cultural and philosophical dimension does not diminish the science, it enriches it. It provides a framework of meaning that makes the cold, hard facts feel personally relevant and emotionally resonant. The science tells us how the nuclear fusion, the supernova explosions, the accretion of planets, but the poetry, the music, and the philosophy help us explore the so what. They help us integrate this incredible knowledge into our own sense of self and our understanding of what it means to be alive in such a universe. It transforms the story of Stardust from a remote astronomical process into a deeply human one, a narrative that connects the quantum dance of atoms inside a star to the beating of our own hearts, and in doing so, makes the universe feel not like a cold, empty void, but like home. Now, the most incredible part of all this is that you don't need a multi-billion-dollar space telescope or a physics degree to connect with this cosmic story firsthand. You can actually go outside and witness the evidence of this grand cycle with your own eyes, and you can do it tonight, stepping out under a clear, dark sky is the single best way to transform this from an abstract scientific concept into a tangible, personal experience, a direct link between you and the distant stars. Your first and most accessible window is simply to look up and find the Milky Way. On a night away from the polluting glow of city lights, our galaxy appears as a faint, ethereal band of light arching across the heavens. That soft, milky glow isn't coming from a single source. It is the combined light of billions upon billions of distant stars, but crucially, it is also fractured and segmented by dark, winding rivers that seem to split the band apart. Those are not empty voids. Those dark patches are colossal clouds of stardust, vast interstellar nurseries and debris fields so dense they block the light from the stars behind them. When you find that dark lane running through the center of the Milky Way, you are looking directly at the raw material of creation, the cosmic flower that will one day become future solar systems. You are seeing the stage where the entire drama of stardust unfolds. To bring this view into even sharper focus, a simple pair of astronomy binoculars is your best tool. They gather far more light than your eyes alone, transforming those faint smudges into detailed portraits. Train them on the constellation Orion, easily found by its famous three-star belt. Hanging from that belt is a fainter line of stars known as Orion's sword. Point your binoculars at the middle star in that sword, and you will see it is not a star at all. It is the Orion Nebula, a glowing, fuzzy patch of light. That faint glow is the combined light of newborn stars illuminating the vast cloud of gas and dust from which they formed. You are seeing a stellar nursery in real time, a place where the cosmic recycling process is actively happening right now, over 1,000 light years away. For a more dynamic and immediate encounter, nothing beats a meteor shower. These are not actually shooting stars at all. They are tiny particles of stardust, often no larger than a grain of sand or a pea, that have traveled across the solar system. When Earth's orbit carries us through the debris trail left behind by a comet, these particles slam into our atmosphere at tremendous speeds, burning up in a brilliant flash of light. Watching a meteor shower is literally watching stardust die a spectacular, fiery death in our sky. The Perseids in August or the Geminids in December are two of the most reliable annual shows. Each streak of light is a direct visitor from the depths of our solar system, a tiny piece of a comet that itself is made of the most ancient, preserved material from the birth of the sun. To navigate this celestial landscape, you have a powerful planetarium right in your pocket. Free mobile apps like Stellarium or Sky Safari use your phone's GPS and gyroscope to show you a live map of the sky above you. Simply hold your phone up and it will identify constellations, point you towards planets, and help you locate deep sky objects like the Andromeda Galaxy or the Pleiades star cluster. These tools remove the guesswork and make finding those faint, dusty treasures a simple and rewarding adventure, turning a casual glance at the sky into a guided tour of the cosmos. This act of engaging directly with the night sky completes the circle. It bridges the immense gap between the atomic and the astronomical, between the science we can study in a lab and the profound wonder we feel when we look up. It transforms the knowledge that you are made of star stuff from a beautiful fact into a deeply felt connection. You are not just learning about the universe, you are remembering your place within it, under the same ancient light that has been fostering new stars and new worlds since the very beginning. So let's bring all of these incredible threads together into a single, cohesive picture. The homecoming of Stardust is a grand, multi-stage symphony, and each movement is governed by its own set of physical laws working in perfect concert. It begins, of course, with the finale of a star's life. Whether through the gentle, persistent winds of a red giant star, patiently puffing its outer layers into space to form a beautiful planetary nebula, or the cataclysmic, universe-shaking violence of a supernova explosion that forges heavy elements and blasts them across light years. The first act is one of glorious, necessary death. This is the moment of release where the star returns its enriched essence to the cosmos, seeding the void with the very ingredients for everything that will follow. Once freed, these particles embark on an epic, solitary voyage through the interstellar medium. This is not a straightforward journey, but a perilous drift across an ocean of nothingness, guided by subtle and powerful forces. The gentle, constant push of radiation pressure from distant stars acts like a cosmic breeze, slowly propelling them forward. The immense, invisible scaffolding of the galaxy's magnetic fields causes charged grains to align and spiral along invisible lines of force. And overarching everything is the relentless, patient pull of gravity, the great architect of the cosmos. This force draws the dust toward regions of higher density, shepherding it into the spiral arms of galaxies and ultimately into the waiting embrace of giant molecular clouds, those stellar nurseries where the next act is about to begin. Upon arriving in the dense, cold environment of a nebula, the Stardust's role shifts from wanderer to builder. Here, the process of accretion takes center stage. In the frigid quiet, particles collide gently, sticking together through electrostatic and van der Waals forces, growing from microscopic specks into pebbles, then rocks, and eventually the mountain-sized planetesimals that are the true building blocks of planets. But the transformation isn't just physical, it's profoundly chemical. These grains become tiny laboratories, their surfaces collecting icy mantles of water, ammonia, and methane. Bathed in the ultraviolet light from newborn stars, these ices are broken apart and reassembled into more complex organic molecules, including the amino acids that are the precursors to life itself. This chemical enrichment prepares the raw materials for the creation of habitable worlds. Crucially, this stardust is not a passive participant. It plays an active, catalytic role in the very creation of its new home. The dust grains are incredibly efficient at radiating heat away from a collapsing gas cloud. This allows the cloud to cool, reducing internal pressure and letting gravity win the battle, thus accelerating the birth of new stars. Furthermore, the surfaces of these grains provide a crucial meeting ground for hydrogen atoms, allowing them to form molecular hydrogen, the primary fuel for stars. Without this catalytic effect, the process of star formation would be immeasurably slower and less efficient. The universe, in its infinite wisdom, uses the ashes of the dead to midwife the birth of the new. This entire breathtaking cycle, from stellar death to stellar rebirth, is not just an elegant theory. It is supported by a vast and growing body of evidence. We see it through the infrared eyes of telescopes like James Webb, which peer through the dust to reveal glowing stellar nurseries. We detect the chemical fingerprints of complex molecules with radio telescopes, and we map the magnetic fields that guide the dust through polarimetry. Most astonishingly, we hold physical proof in our hands, presolar grains found inside ancient meteorites, whose exotic isotopic compositions are a definitive fingerprint, proving they were forged in the hearts of long-dead stars billions of years before our sun was born. This grand cycle operates on timescales that dwarf human history, spanning millions to billions of years, yet it is the very engine of cosmic evolution. It explains the stunning diversity of planets we see, as each system forms from a unique blend of dust from different types of stars. It reveals a universe in a state of constant, dynamic flux, where death and rebirth are not opposites but are inextricably linked in an endless, elegant dance. Every atom in our bodies, every planet in the sky, Every star in the night is part of this story, a story where every single particle has a history that spans the ages, connecting us all to the cosmos in the most fundamental way imaginable. This cosmic cycle matters because it fundamentally redefines our place in the grand scheme of existence. The realization that the atoms composing our bodies were once forged in the hearts of distant, long-dead stars is more than just a beautiful piece of trivia. It is a profound scientific truth that connects every single one of us to the universe in the most intimate way possible. That iron carrying oxygen in your blood, it was likely synthesized in the final moments of a massive star's life before being scattered across the galaxy by a supernova explosion. The calcium that strengthens your bones and the oxygen you breathe with every breath, they too are souvenirs from stellar furnaces that ceased to burn billions of years ago. This isn't a metaphor, it is our biological and chemical reality. We are not just living on a planet, we are walking, talking collections of cosmic artifacts, each of us a living museum of astronomical history. This knowledge dissolves the illusion of separation, revealing that we are not isolated observers of the universe, but an integral part of its continuous, dynamic flow. Scientifically, understanding this cycle provides the essential foundation for virtually all of modern astronomy and planetary science. It answers the most fundamental question of our origins: where did everything come from? Without the life and death of stars, the universe would still be a boring soup of hydrogen and helium, the pristine elements left over from the Big Bang. There would be no rocky planets like Earth, no liquid water oceans, and certainly no chemistry complex enough to give rise to life. The cosmic dust cycle explains the very existence of the periodic table beyond its first few elements. This framework directly shapes our search for habitable worlds beyond our solar system. When astronomers use telescopes like James Webb to analyze the atmosphere of a distant exoplanet, they are looking for the signs of those biologically critical elements: oxygen, carbon, nitrogen, that were delivered to that world by Stardust. We are, in effect, searching for planets that have successfully incorporated the same stellar debris that we did, raising the incredible possibility that we might not be alone in the universe. On a cultural and philosophical level, this story inspires a powerful dual sense of awe and humility. It is awe-inspiring to comprehend the sheer scale and beauty of the process, that within each of us resides the legacy of cosmic events of unimaginable power and grandeur. Yet it is also deeply humbling. It reminds us that our planet, our species, and our individual concerns are all part of a much larger, older, and ongoing narrative. In a world often dominated by short-term thinking and division, this perspective offers a unifying vision. It doesn't matter your background, beliefs, or nationality. We all share the same cosmic ancestry. We are all made from the same stardust, all participants in the same universe. This can foster a profound sense of global citizenship and a renewed responsibility to care for our fragile planet, the only home we have made from this ancient stellar material. The practical benefits of studying stardust are often overlooked but are equally transformative. The quest to understand these tiny particles drives technological innovation at the very edge of human capability. To analyze presolar grains smaller than a bacterium, scientists had to invent incredibly sensitive instruments like secondary ion mass spectrometers, pushing the boundaries of analytical chemistry. These advancements have ripple effects, improving our capabilities in materials science, nanotechnology, and even medical imaging. Furthermore, the effort to collect stardust from comets, as with NASA's Stardust mission, required pioneering new materials like aerogel, the lightest solid known to exist, which now has applications in insulation and particle physics. The challenges of space exploration, motivated by questions about our cosmic origins, consistently lead to breakthroughs that improve our lives on Earth. Ultimately, the greatest gift of this knowledge is the invitation to shift our perspective. It asks us to see ourselves not as passive inhabitants of a random rock orbiting an average star, but as active participants in a majestic, billion-year-old story of cosmic evolution. We are the universe itself become conscious, beginning to understand its own history and its own processes. The hydrogen that formed just after the Big Bang, the carbon forged in a red giant, the iron blasted from a supernova, these atoms have now come together to form a brain capable of wondering about its own origins. We are the universe's way of knowing itself. This connection is not something that happened long ago and far away. It is a living process that continues within us and around us every single day. Every time we look up at the night sky, we are not looking out at a distant, foreign void. We are looking at our extended family, our birthplace, and our eventual destination, all woven together in the endless, beautiful cycle of stardust. As we reach the end of our journey together, tracing the incredible voyage of Stardust from its explosive birth to its quiet, purposeful return, it's worth pausing to reflect on the profound unity this story reveals. We've followed these microscopic particles across light years of empty space, witnessed them being forged in the hearts of dying stars, and seen them gently coalesce in the dusty cradles of new solar systems. This isn't just a tale of astronomy, it's a story of connection, a narrative that ties the grandest cosmic events to the most intimate details of our own existence. The universe, it turns out, operates on a principle of beautiful, relentless recycling, where endings are merely disguised beginnings, and where death on a stellar scale gives birth to planets, oceans, and life itself. This knowledge fundamentally changes our relationship with the night sky. It transforms those distant points of light from mere specks of beauty into active, dynamic participants in our own story. The faint, glowing nebula you might spot with a telescope is no longer just a cloud. It is a cosmic nursery, a construction site for future worlds, bustling with the same materials that make up our bodies and our planet. The darkness between the stars is not an empty void but a highway, filled with countless particles on their own billion-year journeys home. Every time you step outside and look up, you are witnessing an ongoing, universe-wide process of creation and renewal, a cycle that has been running for billions of years and will continue long after we are gone. This perspective is both humbling and empowering. It reminds us of our smallness in the vast expanse of space and time, yet it also bestows upon us a magnificent dignity. We are not accidental guests in a random universe. We are the universe itself become conscious. The iron in your blood that carries life-giving oxygen, the calcium in your bones that gives you structure, the very air you breathe, all of it was once part of something enormous and majestic. A star that lived and died so that you could one day exist. You carry a piece of that cosmic history within you every single day. Our journey through the mysteries of Stardust may be concluding, but the real exploration is just beginning. New telescopes peer deeper into stellar nurseries, and advanced labs analyze ever smaller grains of ancient meteorites, each discovery adding another piece to this incredible puzzle. The quest to understand our cosmic origins is one of the greatest adventures of the human spirit, and it's an adventure in which we can all participate. So the next time you find yourself under a clear, dark sky, take a moment, look up, marvel at the knowledge that you are made of the very stuff you are gazing upon, and that you are forever connected to the grand, beautiful, and ever-turning cycle of the cosmos. Thank you for joining us on this exploration. If you have thoughts or questions, we'd love to hear them in the comments below. And if you want to join us for more journeys to the edges of understanding, be sure to subscribe. Until next time.